Nobody has ever seen a back test that doesn't look spectacular. It never gets presented. So,
And you mentioned, the methodologies evolved as well. You mentioned bag of words, kind of the classical NLP sort of technique. I mean, are you finding people are using LLMs themselves to extract the sentiment, or is it more sort of Finbert models?
The problem with using off-the-shelf LLMs is that it's not possible to get an actual point-in-time estimate, right? So, for example, if I run the transcripts, I can take a transcript from 2018 or 2019, run it through ChatGPT or one of the other LLMs. It has access to what happened after that, right? So I've read some academic folks have tried hiding the names of the company, et cetera, et cetera. So we don't follow that path, right? So we will use techniques that go behind LLMs, right? So for example, neural nets and so on, right? So that kind of those methodologies are used, but we will end up applying those, or the methods of the firms that we work with will apply those without a look-ahead bias, right? Without using the classic LLMs. So some of the technology, some of the methods might be common, but we are not using sort of just off-the-shelf LLMs.
And presumably that makes a big difference then for your back test, because if you have look-ahead bias, presumably your results will look fantastic on the back test, but in practice, it will fall down quite quickly.
Absolutely. One of my colleagues always says that nobody has ever seen a back test that doesn't look spectacular. It never gets presented. So yes, absolutely. And that is one big issue. It's always an issue in any quant strategy, but I would say if in application of AI and ML methods, the tendency to just have a look-ahead bias or to overfit and show a rosy back test, which then obviously will disappoint, I think is a big risk. It's a much bigger risk than in traditional statistical methods.
And, we're talking about back tests here. I mean, another challenge, of course, is the feature engineering or the feature selection. People call it AI, picking the right variables, people who are more used to sort of, statistical sort of techniques. So what's your approach to sort of picking the right features? Because again, you can go crazy on this and just throw everything and there's lots of biases you could introduce here as well.
Yeah. So the feature engineering side, we sort of put that as a distinct pre-step to the model training, right? So yes, we recognize that the feature engineering is very critical, and there are different methods that get used for that. So what we typically do is, rather than throw in all the features into the model and let the model train and sort of do the parameter tuning, etc., is we will use dimensionality reduction, clustering, and there are different methods that we use to get the feature set down to a smaller number. But importantly, we do have humans review the output from feature engineering to see that we are seeing a sensible set of features where we do believe there is a causal relationship with the hypothesis that we are testing. So we start with the hypothesis or the problem solving. We've looked at the data which we believe will fit into that problem solving framework. And then we let feature engineering come up with a list of features. And why that has become even more critical is because the number of features has exploded with inclusion of alternative data sets. And so it makes the feature engineering very critical. And a very important step with a lot of human expertise, again, is to review those. And then once the feature engineering step provides us with a sensible sort of list of features, then we go to the next step, which is the model training.
And you mentioned reducing the dimensionality, and clustering and so on. Do you find that the unstructured data, such as like sentiment measures on transcripts, do some of them cluster with the conventional data itself? Do you end up with a sort of a mix of unstructured data, conventional data sometimes being grouped together, or are they always orthogonal from each other?
So I think what we find is where data tends to group together is based on the investment horizon. Right? So if you are if, for example, in our startup strategy, where we use a significant amount of alternative data, our horizon is shorter. It's a few weeks, is a week or two to max 3 weeks, right, for the different signals. So if you look at the kind of data that is used for that, that doesn't align as well on that horizon with the traditional data. But when we are testing out the data sets, right? So, for example, if you're looking at quarterly changes of revenues or sales, we will make sure that our data sets help predicting that, although we are looking for our horizon tends to be much shorter, right? So, a lot of the clustering we find is from features that are help in explaining returns or most of the time security pricing over a 2 to 3 week horizon. If we do that with some of the longer term horizon strategies that we run, I think what you mentioned could potentially match. But then there are fewer alternative data sets that lend to that horizon.
Yes, yeah, of course. And then in terms of models, I know you kind of were saying it's very fun to play around with the latest models, and I like playing around with the fastest, latest models and so on. But which ones do you tend to end up relying on? So obviously, I imagine there's the econometric models, the classical statistical models, on the one hand. Then on the machine learning side, do you end up veering towards random forest and gradient boosting models, which typically have been known to do quite well? Neural nets, while people try to use that, it tends not to be as powerful sometimes as people think. What's your experience of what you end up using?
So, we sort of divide those into three different model categories. So the linear models, right? The ones that
linear models, yeah.
got to that, right? So the econometric, sort of the older sort of statistical methods, linear models, decision tree based models, right? That we use, and then the neural networks. Our approach has been to ensemble the models using the different models. And the reason for that is we don't believe in investment management, certainly in quantitative equities, the field that we specialize in. There is enough out of sample evidence in terms which models work. Yes, there is research in terms of back tests to determine which kind of models work in different situations. We do have our view as well. But what we have been doing is over the last several years is collecting a lot of data on how each of these types of models have worked on an out of sample basis. But we need to see more evidence as a quant. And so our approach right now is, yes, we do have views on certain kinds of problems which might work better, but we are avoiding the tendency to sort of over concentrate on one method versus the other. Our effort really goes in, right? So I spoke about sort of the data part and the feature engineering. Within the model training, there's a significant amount of effort that again goes in evaluating the model in terms of its forecasting ability, the set of features that it picks up as finally being important. And that is a challenge with machine learning AI methods because it's not always immediately evident, right? At least so, for example, in terms of neural nets, right? How do you necessarily come up with the feature list the way a linear model would show, right? That's clearly not the case. So I think that's where we tend to spend the most of our time, that we are not sort of how is the hyperparameter tuning being done, and how are the model parameters, how often should we need to train the model. But once we have done that and we feel that the model sort of meets our rigorous standard, we would tend to combine multiple models, even if the backtest shows there are clear preferences for one versus the other.
And, you kind of mentioned this, that, the machine learning models tend to be a bit more of a black box. It's hard to really understand why they're behaving the way they are. And so there's been various different attempts to make them more of a gray box or white box. One is Shapley values. Seems to be quite promising to kind of understand why it made those decisions. I mean, how do you go about, trying to make things more transparent?
So I think it really starts with the problem framing and the data selection part, right? So we would our problems framing is based on hypothesis driven, so it's economic hypothesis driven. The data that we selected, we will have a prior sort of a causal relationship, right? So for example, if you're seeing a credit card transaction, we use credit card as an example, right? Credit card transactions pick up, that should be good for sales for that particular company. If the earning transcript sentiment scores are trending higher, and that company transcript shows that the management is more positive than other companies, that's a positive thing. So there is a causal relationship, and the feature engineering again sort of makes an attempt to do that, right? So yes, by the time you train the models, it's getting harder and harder as compared to the statistical methods. But through just sheer using it and focusing on a lot of the research that is coming out in these areas on how to evaluate and how to sort of try to explain that in regular terms, in traditional terms rather. I think there's a lot of effort that goes into doing that. But yes, it's not quite to the level that you have with the regular, the traditional method. And I think it becomes most relevant when the strategy is not working. And when things are working well, investors, everybody sort of is sort of aligned and happy in that regard. But when things are not working well, it does become a challenge to how to be able to explain to ourselves and to investors that the strategy is doing what it is meant to do. And I think we're getting better at that. We're getting better at that, certainly.
Yeah,
but that's one of the challenges.
Yeah, no, I think your approach is a bit different to many other AI type, fund managers that I know who are more of the school of like throw all the data at the model, and then they end up having this problem of trying to understand the model. But because you do a lot of this earlier stage work in trying to understand what are the relationships, what's your hypothesis, causal relationships, then you kind of reduce the issue of trying to understand what the black box is doing, so to speak. So a lot of people, I mean, the AI mindset is throw all the data in and the model will kind of work out the relationship. So it's kind of model first approach rather than the data and the hypothesis.
Yeah, and I think I actually think that yes, that is how a lot of folks who sort of communicate that. But I do think that folks who have been, not just in investment management, but broadly, who have been more successful at implementations, and we see there's a big difference in implementation, right? Whether it's in investment management or otherwise, they do recognize that that approach does not work as well, right? So for us, it's not just about being able to explain. Yes, that's an important criteria, but we think that the risk of overfitting goes up dramatically. Looking for strange patterns, etc., goes up dramatically when you throw just data indiscriminately at the models. That's been our experience, and we find that a lot of the 99% of the research papers on applying AI and ML to the investment management problem do essentially that, right? Just throw a lot of data, and when you try to replicate them, the out of sample results are just not.
Yeah, no, I totally agree.
Good, right? I think that's really what is stopping us, right? It's not a philosophical, although in some ways it is, but it's really, we don't think that approach works for successful investment management.
Absolutely, yeah. Almost every day I receive some paper sort of saying I've applied AI to equities and my Sharpe ratio is 3, and this is the new revolution.